and we worked under the guidance of Dr. Carrion along with our colleague Brian Ludwigson. Today we're going to discuss with you our efforts on the research of the synthesis of hydrozones as antibiotics. Before we begin, I'd just like to give you a brief background on what an antibiotic is and why we use this combinatorial component. So what exactly is an antibiotic? An antibiotic is a chemical or a substance that will either kill live bacteria or inhibit the growth of bacteria. The first antibiotic to be discovered was in 1928 by Alexander Fleming, and this antibiotic was penicillin. These are some two very common antibiotics that are used today. On my left here, we have amoxicillin, which is the generic for amoxil. And on the right here, we have azithromycin, which is the generic for Zithromax. You may also know that better as a Z-Pak. So what exactly is the importance of antibiotics? Well, antibiotics can differentiate between the structures of the host cells and bacterial cells. They can prevent the proliferation of bacteria, and they can do this in several different ways. For example, one of the ways they can do this is by inhibiting synthesis of cell walls. Additionally, a key factor is that antibiotics are not used to treat viral infections. They are specifically geared towards bacterial infections, which is why, for example, if you have a cold, you're not going to take an antibiotic for this. Additionally, you're not going to be prescribed the same antibiotic for every bacterial infection that you have, which is why there's such a broad range of antibiotics out there, depending on what you are diagnosed with. Again, antibiotics treat infections in several different ways, inhibiting cell wall synthesis, inhibiting protein synthesis, interfering with metabolic processes, and nucleic acids. Now, what exactly is combinatorial chemistry? Well, the purpose of combinatorial chemistry and the advantage of it is that you can make a large library of compounds versus individually purifying and laboriously purifying each one and screen them for biological activity. We were concerned with the antibacterial growth. And another thing is that you can create these libraries in a very short time frame. And just to give you an idea, we were able to synthesize 28 compounds in a 3 to 4 hour time frame. A prior researcher, Joanna, verified this lab 3 years ago. This is a general reaction scheme for the synthesis of hydrozones, and this shows how we prepared our 16 different hydrozones. More specifically, A1 through A4 are the aromatic aldehydes that we used in this study. A1, A3, and A4 are benzene rings substituted with an electron withdrawing nitro group in the ortho, meta, and para positions. A2 is not a benzene ring, but a furan ring. And B1 through B4 are different hydrazine derivatives that were used in this study. Of the 16 compounds that we tested, it was determined that our active lead compound was guanofuracil, seen here. This is a general reaction scheme for the synthesis of hydrozones. And you can see this reaction scheme that was prepared via a nucleophilic acyl substitution by treatment of commercially available 5-nitro-2-furaldehyde with aminoguanidine in the presence of acid to give this corresponding compound, hydrazone 3, of guanofuracil. I will now pass this over to my colleague Mike, who will discuss our research.
So, just like Nicole said, we want to know what makes a good antibiotic. And hydrozones are a family of compounds that display a wide range of biological activity, including antibiotic activity. So like Nicole said, prior research in our lab has shown guanofuracil, this structure here 3, to be our most active compound. And so last year we worked with a former colleague, Marty, and we asked ourselves, how can we vary this structure to find a more active antibiotic? And so Marty now is actually studying at the PhD program at Syracuse University, and we asked ourselves, in varying this structure, what are the different aldehydes that we can use? And in order to do so, we had to turn to synthetic organic chemistry. And so these are the 6 aldehydes that we studied last year. As you can see here, 5-nitro-2-furaldehyde was our most potent aldehyde. And so we varied it with various chemical structures. So for example, here this is a pyrrole ring. The central atom is replaced from oxygen to nitrogen, and the nitro substituent is removed. And so we did the same thing here. We replaced the heterocyclic ring with a thiophene ring, and the central atom oxygen is replaced with sulfur, and the nitro electron substituent is removed. Here we kept the ring the same, it's a furan ring, and we removed our electron withdrawing substituent. And the bottom line is what we found last year when we worked with Marty is that guanofuracil was still our most active hydrosome. And so we asked ourselves the same question this year. We're going to vary our aldehydes and screen them for biological activity. And so we tested 28 different hydrosomes, and this is, like Nicole said, the general scheme for the synthesis of a hydrosome. We have an aldehyde plus a hydrazine in the presence of acid to give us our hydrosome. So these are the 6 different aldehydes that we studied this year in our lab. As you can see, the benzaldehyde structure is exactly the same, but what we did was we varied our substituent at the pair position, or the 1,4 position, with various electron donating and withdrawing groups. And so, for example, we have fluorine here, methyl, hydroxyl, and dimethylamino. AA1 through AA4 are 4 aldehydes, and these are all electron donating groups. And in AA5 and AA6 we have chlorine and bromine respectively, and these are electron withdrawing groups. And so this is a deconvolution of our results. Deconvolution is just a method in which we can interpret and analyze our data. And so what we do is, well, also as Nicole said, combinatorial chemistry usually puts a graph to combinatorial chemistry. This allows us to generate a large library of compounds without synthesizing every single compound individually. So it's much more time efficient and allows us to eliminate waste, some great chemistry principles. And so we make this table, we just follow a standard protocol to analyze our data. And so what we do is we line up our seven mixtures here, and among them, mixture 5 was our most active mixture. It inhibited the growth of bacteria the most. And so we highlight that across. And what we do is from M8 to M11, we do the same thing. M10 was our most active mixture, and we highlight that down. And that will land us at our most active compound, A2B3. The A represents the aldehyde, and the B represents the hydrazine. And so our A was 5-nitro-2-fluoraldehyde, our hydrazine was aminoguanine, and in the presence of acid, they give us guanofuracil, our most active compound. And so this is exactly what we did in our lab the entire year. These are our results. What we did is we grew our bacteria, we made the wells, and then we administered our hydrosome. And then we will put it in the incubator and come back 24 hours later and measure our zones of inhibition. So you can clearly see here by the yellow and the green arrows that these zones are shown around the wells. The larger the zone, the more inhibition, the greater the antibiotic activity. So you clearly see that some of these mixtures were much more effective than some of the other compounds that we studied. So I think this is a really nice graph that shows all the aldehydes that we studied this year and their corresponding zones of inhibition. And this is 5-nitro-2-fluoraldehyde, which was our most active aldehyde with close to 9 millimeters. And so in conclusion, what we did a few years ago was we worked with our researcher Joanna and verified this lab. The last year was our first real research component in that we varied our heterocyclic structure and we found guanofuracil to be our most active compound. This year what we did was we varied our benzaldehyde with various electron donating and withdrawing groups at the pair position, and we found that guanofuracil was again our most active compound. And so what I think makes our lab really unique is that it shows the importance and integration of biology and chemistry. And while the study of living systems is surely biology, our understanding of atoms and molecules is undoubtedly chemistry. And finally, we'll actually be able to incorporate this into our bioorganic lab curriculum here at Rampo in the fall of 2015. And I think that's something that we can be really proud of. And so for the future, what we hope on doing is to continue to ask ourselves, can we still find a more active compound than guanofuracil? And in doing so, we'll continue to vary our benzaldehyde with various electron donating and withdrawing groups. And in addition, we plan on synthesizing guanofuracil by itself and screening that for antibiotic activity. And that will really allow us to compare this pure compound with our combinatorial mixture that we made this year. And this will really allow us to see what exactly is inhibiting the growth of the bacteria. Is it the pure compound guanofuracil, or was it some other byproduct of our mixture?
And of course, now to one of the most important slides, the acknowledgments. We'd like to thank the TAS Research Honors Program and especially Dean Safe for giving us the opportunity to do research for the past 2 years. A huge thank you to Dr. Tom Owen for his collaboration and assistance with cell culture, for troubleshooting any problems that we came across. Our fellow researchers, Sean and Chris, the chemistry and biology lab coordinators, and of course the NSF-sponsored Green Chemistry Workshop at the University of Oregon, for giving us the inspiration to do this project, which we were able to verify and then turn into our own research. And of course, thank you to you, the audience, for providing us with your attention, and now we'd be happy to answer any questions.
What kind of bacterial system you use for the antibacterial activity assay? What kind of bacteria do you use?
E. coli.
E. coli.
Yeah.
So that's the only system you use.
Yeah. I actually thought about switching that for next year and trying different types of bacteria.
But maybe it's not too much, but do you have any idea how they get the bacteria or this mechanism?
We didn't look at the exact mechanism of inhibition. We kind of focused on just understanding which chemical structure inhibits it, and then I guess maybe later we can ask why and how.
What about DMSO itself? Does it kill the bacteria?
No, we actually tested that by itself to make sure that it doesn't, and it didn't. We used DMSO for solubility issues that we had when making our mixtures, but in terms of inhibiting the growth of bacteria, we can say positively that it didn't affect it.
That's very toxic bacteria.
Yeah.
Okay.
How toxic, I'm not sure if you know, but how toxic would this be to eukaryotic cells? Is that-
I don't think it's going to be really considered. We can discuss that with our advisor, and we'd be happy to address that in the poster session for you after.
We can ask Dr. Buck.
Or Dr. Rob. Yes.
Following up on the same theme, I think this would be really valuable if you could start testing different types of microorganisms. You're building up sort of a two-dimensional model of how the chemistry affects this particular organism, but you could go to a three-dimensional model where you're having different attributes of the organism, add a third dimension into how your chemistry is affecting things. I think that might be really insightful into how things are actually working.
Thank you.
Thank you.
You had a nice graph with the activity depending on the element. This one.
Yeah.
You see that the fluorine, chloride, bromide, all of them kind of have lower activity, and you can follow with the periodic table. Fluoride is the most reactive. Have you checked the stability of with time of your antibiotic? Is this after 24 hours you still have the same compound when you put fluoride?
Yeah.
Thank you.